Next speaker, I'm very pleased to announce, is Falko Schmidt from Gothenburg University, and he's going to tell us about self-organization colloidal systems in the presence of fluctuations.
Please. Thank you, Marco. Good morning, everyone, also from my side. I want to thank the organizers, first of all, for giving me the opportunity to talk about my previous work. I'm split my talk into two parts, basically. First, I will show you that using passive, just Brownian particles, and light in a critical system, you can induce active colloidal molecules. And in the second part, I want to focus a little bit on feedback-driven systems using also droplets. So we combine droplets and colloids together. To give you a bit of motivation for colloidal molecules, so this principle is not new. It has been done now a decade ago using just passive particles that you combine with DNA patches. Of course, the system is intrinsically passive, so in order to get it out of equilibrium, you need to drive it through an external field. You can exchange, of course, these passive particles now with just Janus colloids and make them active just by that. An alternative approach was basically presented by Soto and Golestanian in 2014, where they use two species of passive particles. One is chemically active, the other one is not. And then they come together and form different types of colloidal molecules, which show different types of activity. And the first experimental realization was done by Neo and co-authors, where they have this ionizing system that is basically fuel-driven, and it's kind of like a predator-prey behavior, but it shows already some of the characteristics, but not all of them. And what I want to show you is now that we are able to use light to induce the spontaneous self-assembly of such colloidal molecules. And we're going to look at how the molecular structure basically gives different types of activities. What I'm going to show you is now the experimental image and some snapshots to it. We also did simulations in collaboration with Benno Liebchen, who was a postdoc at the Hartmut's Löwens group at that time. And we have two species. In our case, they are light absorbing. They're a bit darker. And we have non-absorbing ones, which are a bit lighter. And when I play the video, you will see as soon as we turn on the light, these particles will come together, and in its simplest form, they will form a Janus dimer, kind of like a Janus particle, just made out of two particles. And over time, these molecules start to grow. More and more non-absorbing particles will come, and then the activity will change over time. And you see that this one slowly starts to rotate, for instance, where you have also the more non-absorbing particles come, the more radiosymmetric it's going to be. It's becoming also then more static. Interestingly, as soon as you turn off the light, of course, you take away the energy into the system, and therefore they just become Brownian particles again. Now you can turn the system on again. You can repeat this continuously, and you would form active colloidal molecules over and over again. The way it works in a kind of sketch system, so in the experiment, what we do is we basically confine these colloids into these. So we put two glass cover slips on top and on the bottom. And what we then have is, as soon as we turn on the light, we basically heat up the light absorbing particle. It creates a thermal gradient into the system. And eventually, since we have a critical system, also a diffusive motion, and this will bring our particles together. So this is what Clemens Peschinger should know already. We have this critical system. So by temperature, we can basically go into the other phase of the system, the demixing phase. If you're close to the critical point, you can immediately transfer forth and back. In simulations, what we can now understand is, and this was done again by Benno Liebchen, basically, if you have a non-absorbing particle that is close to an absorbing particle, you break the radial symmetry of this particle, and therefore form kind of like a Janus particle. That's why we call it a Janus dimer that is then able to propel in space. What we also observe is the more particles come together, you get non-reciprocal forces that start to add up. That is because you have this kind of overlapping angle. And in the end, you can get like a whole slew of different types of molecules. They can be immotile. Then you get these what we call migrators. These are ones that mostly move straight. If you start to have something that's a bit more radially symmetric, they of course stop moving. But you can also have different types of rotation, like spinning or orbital kinds of rotation. So I've shown you now one system that is self-organized. Of course, there are many other examples that have been shown using colloids, but also droplets can be used, and I think Corinna will talk much more about this. But even Janus droplets can be used to propel in space. What I want to put a bit more attention on is this kind of droplet. You can't really see it, but there are bacteria included in this. I think it was an oil droplet, and then this droplet starts to spontaneously move. And it's kind of a nice system because you start to combine active agents with droplets. But what all of these systems have in common is that they use the environment as a free energy source to mediate any kind of interactions between the active agents. And we've heard a lot during this conference. They can be hydrodynamics interaction. They can be based on visual perceptions, as we heard yesterday from Massimo, by birds, acoustic, or in most cases, I think we discussed chemical and electrical fields to propel our particles. But what they're all missing is an intrinsic feedback mechanisms between both systems, so between the environment and the active agents, and then something that mediates also back to the environment. And this is what I want to show you, basically. We call this system now active droploids, which is a portmanteau of droplets and colloids. And I want to show you that feedbacks are an important feature in the system for the self-organizations, and we're going to characterize it a little bit. So the video it looks very similar because it's the same kind of system. All we're doing is we're putting more energy into the system, which is basically by putting more light intensity. And what you see at the beginning, again, we start with brownium, we get our active colloidal molecules, but it's a little bit later, you start seeing droplets forming around it. Interestingly, these molecules, they still stay and they still move around. And while they move around, they move the droplet with it. So they still influence their local environment. And over time, if you would watch this more, it would be like a gigantic droplet being forming. And this is what we again see in simulations. We've done that again with Hartmut and a PhD student of his. And just to have a look at the feedback mechanism. So we have the environment. That's again our critically demixing system. The difference is again that we're demixing the system much more than we did before. So we're far away from the critical point. And the usual mechanism is, of course, that the environment first provides the aggregation of the colloidal molecules, the particles into colloidal molecules, but it also provides a confinement because particles cannot escape the interface of the droplet. That's why they're always staying inside. On the other hand, the colloids, while they're moving, they induce a motility of the droplets. Yeah? So there's an intrinsic feedback mechanism that then creates our new kind of structures that we're observing here. And if we look at the phase diagram, what we're doing is basically this is the energy input, which is on one hand the light intensity, but it's also the density of absorbing particles. Of course, the more particles you have that absorb, the higher the temperatures. And then we look at the relative concentration. So before we always looked at a fixed concentration close to the critical point. What we do is now we move a little bit away and create an energy barrier in effect. And we have these four phases. The first one is, of course, just brownium particles. You're not inducing anything. Then we get the ones we discussed in detail already, the active molecules. Now we're coming into the interesting one. So if you induce more energy into the system, what we see is then these droplets starting to form with the active colloidal molecules inside. And if you put even more energy, what happens in our system is that suddenly these two species of particles, they split apart. And of course, I mean, the non-absorbing ones are now decorating basically the interface of the droplet. And if you do that, they break the colloidal molecule, which then breaks down the motility of the droplet in general. And what the simulations allow us to do is actually have a much closer look at the concentration profile in such a droplet than we can do in experiments. And what you see is that there's quite a shallow gradient towards the interface, and this is basically the outside. Since our particles are hydrophilic, we have a water content inside. In principle, you can do the opposite as well. Interestingly, though, now that we induce we put more energy in the system, we start to demix it more, which means we are driving lutein out of the droplet and water more into the droplet. And since our non-absorbing particles are only weakly hydrophilic, they will move to the interface. And this breaks it. All right, let's have a look a little bit about the dynamics of these active droploids. If we look at it, the droplet size, basically we're looking at the growth of these droplets over time. We see that very early on, we have just a diffusion limited growth process. That is that it scales with t to the 1/2, and that is the time when an active particle starts to induce this droplet. So diffusion makes it grow. But over time, if you have your active colloidal molecules inside, it's almost a ballistic growth. Yeah? And with also, again, you see here t to the power 0.4. It's a bit slower than a ballistic growth because you have basically competition between multiple droplets. So they take basically water content away from each other and have to compete. So that's why it's a bit slower than what you would expect with just ballistic growth. On the other hand, it's still much faster than with just a diffusion limited coalescence of particles where we have Brownian basically droplets that start to merge over time and get larger and larger, which is just scales with T over 1/3. All right. Well, interesting what we observe now as well, if you go far away from the critical point, which means you increase the energy barrier to actually go into a demixing regime, so to speak, you see a huge delay in time because you need to put more and more energy into the system. It takes some time until you heat up your environment, but then you see a sudden rapid, we call it almost explosion-like droplet formation that we see in this case. Similar to what we've seen for active matter system, like with Janus particles and etc. If you just put in energy into the system, you look at the velocity, it's not just constantly growing and growing. No, there's actually a turning point eventually. And if we look at basically the number of non-absorbing particles at the interface, then we can get an idea why that is. Because the more you demix, you start to get this much stronger gradient inside the droplet itself. You break basically the activity of the particles, so a droplet, and therefore you get a much lower speeds again. With that, I want to kind of summarize what we've seen. So first of all, I showed you that with these two passive species, we can have a reversible self-assembly process between these two building blocks. But the take-home message is that we actually observe a two-way feedback in this type of active matter system, which is something that has been observed in nature as well. Like our bodies, they perform homeostasis. That is, the cells perform these kind of feedback loops, which can be positive, negative. And so I invite you to take this. Maybe this is one of the realizations, and have a closer look at the intrinsic feedback mechanisms that happen between active agents and their environment. With that, I want to acknowledge the group I've been working on mostly during my PhD. My collaborators, Hartmut Löw and Benno Liebchen, and his PhD, Jens Grauer. And if I invite you to have a look at the two papers that we published on this. And with that, I want to thank you for your attention. I've been quite fast, eh?
Plenty of time for discussion.
Great.
Questions, please. Yes.
What would change if you would change the surface tension of the particles? I mean, if, for example, if you make them very hydrophilic or very hydrophobic so that they would not go at the interface?
Yes, so I would expect that we don't see the immotile droploid phase that we see. So we just keep the active molecules. We can do the opposite as well. If we go to the other side of the phase diagram, we can have very hydrophobic particles inside lutein droplets, and we can see the same effect. If you mix either one of them, then you basically have particles outside the droplets, and you won't see any activity at all.
Questions? Yes, Ricardo.
Hi. I have a tricky question, so don't get me wrong on that. But I'm wondering, why should we call these molecules colloidal molecules instead of small aggregates? What is the piece of definition that makes it?
I think it comes back to the concept that you have two types of particles, or two species of particles, and that you start to make like different functionalizations in a way. So you have one active part and one non-active part, and this kind of could, I mean, in a very, very, very simplistic way, for example, a colloidal molecule. And I guess originally it started from the kind of shape that you could get with just simple colloidal molecules. So they were just reproducing the shape. And I think that's where the term comes from originally. And then it has developed into more structures like that.
I was wondering if there's an analogy to chemical reactions that could break the bonds between the colloids somehow, that could, make it even closer to what we think about for molecules.
And I think people do that. I mean, there are reaction processes that happen, especially with droplets. There's a group around Zwicker in Dresden, I think you might be familiar with, and they do a lot of these reaction-based processes with just droplets. And I think there's a lot of interesting dynamics that happen there as well, like sudden breakdowns, like splitting of droplets into two and etc. So combining these two systems would be a very nice way to continue this work.
Cool, thanks.
Yes, Francisco.
You steer your trajectories using some kind of like patterning or something like that.
I mean, I think Frank and Clemens have shown ways where you could actually, start to use light as a guidance. So instead of, because what we do is basically just a homogeneous illumination of light. So we illuminate the whole area, but you definitely could start to steer them in any way you want by just using spatial light modulation.
More questions? Yes.
Sorry, so I didn't really understand the thing for passive particle stabilizing the interface so much. So you said when you get these immotile droplet phases, there's more active particles in there and they create like a higher energy input and you have a more clear, distinct interface.
Yes.
And then you have the passive particles and they sort of also stabilize the interface, so that stops it from moving. But if I understood correctly anyway, so then it seemed like in the picture, at least, there was just like one part of the interface which was stabilized, which I would have thought meant that the rest of the interface is still relatively, if I don't understand why.
I'm not sure I understand the question right, but you mean like that it's not completely decorated by particles?
Yeah.
I mean, we observed that if you increase just a huge density, and then you can just have like almost like a Pickering emulsion where you have like these non-absorbing particles decorating the whole interface of the particle. That is possible, but it did not have any effect on the dynamics that we've seen. So especially what we had a look at, we thought that might influence the fusion of multiple droplets, especially if you had two of them completely decorated, but we didn't see any effect so far.
No, it's like if you were only decorating a small part, I thought that would be more asymmetry in a way, essentially.
And no, because the asymmetry is very local.
Okay.
And so you create it really in the vicinity of the colloidal molecule itself. Yeah.
Any other question? No, I don't see any hands. So it's time to thank Falko one more time. Great talk.